Okay, hello everyone. Let's start the class today. Let me share the screen. Great. So today we are talking, continuing our work from previous time. We talk about divide and conquer relations and recursive algorithms that happens. And in particular, we talk about Akra-Bazzi or Master Theorem. Generally, when we want to solve a problem, which is has size n, a good example would be for the merge sort. So if you consider that we discussed previous time, so you have an array of size a, size n, and you want to solve, sort this array or do any other operation. You may generally break down these guys into smaller pieces. And then, so this is the part that we will call it divide. And in some sense, we are solving each of these things separately. And then we have, so divide and conquer. And then finally, we have these operations that we are merging these things. Or combine, I will say. Merge or combine. So then we get essentially, say, for example, the sorted array here. So this is the algorithm that we will consider essentially divide and conquer. And it is important that in this, there are some cases that it might be the case that these things that you are dividing are not completely disjoint. So you may have this one, maybe you have this one, maybe you have this one. So this part that we are doing are not necessarily disjoint. They may have intersection. And this is generally divide and conquer algorithms. And this Akra-Bazzi or Master Theorem that we talk about it is the way to solve this problem. We have done similar analysis previous time, but let's start for this case. So, and this is a general way to solve lots of problems. Even for big data, we are using this type of algorithms to solve a big data problem. So assume that the subproblem, so you have a problem that you want to solve. We have a subproblems, and each of them is 1 over b of fraction of the original size. And then to combine the solutions of these subproblems, we need to pay this running time Cn to the k. So if you have such a procedure that you have a subproblems, you need to solve each of them, and the size of them is 1 over b, as I mentioned. 1 over b is not b is not equal to a. Then you need to combine them, and then the running time of this algorithm would be something like this. T of n would be a subproblem, each of them size n over b that you need to solve, and then Cn to the k, that's the one that you need to do it to combine the solutions. This is the one actually that we have done it previous time for a previous problem. In particular, for this formula that we had it previous time, an is equal to 2 times an over 2 plus n. And we have done the analysis in the previous lecture, if you remember. So, and it was a general idea that you are trying to expanding it. Maybe we are putting it n, we are assuming it's 2 to the k. We find a good guess out of all these techniques. And then when we have the good guess, then we try to prove it formally by induction. Now, this, of course, we have done it, but we can do it more generally for these formulas. So there is this that, I mean, you can try actually obtain this, and it's a good exercise for you. But in general, we have this theorem that if t of n is equal to this, for integers a greater than 1, b greater than or equal to 2, and the positive constant c and k here that we have, then this is the running time of these algorithms. What is the running time? The running time, if A is greater than B to the K, it would be N to the log A base B. If A is equal to B to the K, then it would be N to the K times log N. And if we have A less than B, then it is N to the K. For example, if you are considering the previous case that we had it, like this is the same formula that we discussed before. So these are the same things. In this case, so what is A? A is 2. What is B? B is 2 as well. And then what about C? C is 1 here, and K is 1 as well. So in that case, because A is equal to B to the K, which is essentially A is equal to B and K is 1, then we have this second case that we get N to the K where K is equal to 1, that we get N log N. So this is a theorem that actually you can use it and solve I mean, this recurrence formula that often happens in divide and conquer algorithms nicely and get it. Now, there are some other things. This is a general theorem that would be enough essentially to do lots of these things, but I want to say a little bit, some more wording about it. What else do we have it? Again, the proof of this is essentially by induction. You can do it. However, here a theorem which is called, it's the same thing, but instead of this C and K, instead of this C and K, we will have it just f of n. For lots of applications, actually, this C and K is the one that we are doing because it's some kind of polynomial time algorithm that we need to run it. But in general, if you want to do it more, I mean, if you want to get exact and for different K's, not just this one, f of n, then in this case, you can actually, the one that instead of this, we are just saying for general f of n, this is called the Master Theorem. Also, one other thing in the Master Theorem, it says that all of these O notations actually are not just O, these are also theta, which is very important. So that's the one that is the Master Theorem. So we are replacing this one with f of n. And for all of these guys, we have, instead of O, we have theta. So we get exact solutions. There is also one other generalization called Akra-Bazzi theorem, which is the same as here, but you don't have these 3 if cases. It's a more general case that actually contains all 3 cases in one statement. This is the one that is called Akra-Bazzi theorem. So you can see that this is the theorem that we needed in this class, say with the O notations only. But Master Theorem is the one that you have that one. This is more general f of n, and these are thetas that you can also see it in the Wikipedia. And finally, Akra-Bazzi, which is not these 3 cases, all of them considered essentially in one formula. That's the one that is Akra-Bazzi theorem. Good. So that's the one that is actually very useful for the operations that we are having. And now let's go and discuss some other. Another formula that will be very useful for analysis of algorithm. Then we have this kind of recursive relation with full history. So here, the one that we have discussed so far, for example, f of n is equal to, I don't know, some function of f of n minus 1. Or sometimes we have f of n over 2. Maybe f of n minus 1 plus f of n minus 2, and so on and so forth. But it's not the full history. What is the full history? Is the one that f of n, this is like the, when you want to get f of n, this is actually a function of all previous values. So different f of n minus 1, f of n minus 2, and so on and so forth. Up to actually f of 1. This is the one that is called, I mean, essentially a full history recurrence relation. And the way to solve this one is that it is a technique which is called elimination of history. What is the idea is that we try to actually eliminate the history, and we get the formulas which are more like this type of forms or this type of form that we have some solution to solve. Let's see some examples. For example, if you have this simple formula, T of n is equal to this, C plus I equal to 1 to n minus 1 Ti. And note that in general, we have a sigma that we say I equal to 1 to n, some formula AI. We have also these other operations like this means if we have, for example, a set, we generally say equal to 1 to n AI. What's the meaning of that here? If the AIs are the set, means that take the intersection of all of them. Or you may have the same formula actually with, instead of this, you may have the union of them. So we have this general way of writing it. So if this is a product, also we may write it as a pi, for example. Or other things. Good. Now, here we have this formula that we want to solve. And how can we do that? So we can write this formula. This is for Tn that is written here, and say generally for this one, because it depends on the previous one, still we need to have the base case, T of 1 equal to C. So we can write T of n plus 1 as this, C plus I equal to 1 to n T of I. Great. So here, the only difference between these guys is goes to from 1 to n minus 1. These other guys to this n to 1 to n minus 1. This is from 1 to n. Now, what can we do from this formula? This is the full history. Depends to these things. This is the one that we call it elimination of the history. So let's just consider Tn plus 1 minus T of n. So if we do that, I mean, if we just do just Tn plus 1 minus T of n, of course, the left-hand side would be this. What about the right-hand side? Everything will be canceled out except T of n that it remains here. So we just do this one, and then we have this formula. And then we are done, essentially, because in this case, T of n plus 1 is equal to 2 times T of n. And this formula, now we can use it, for example, all of this, for example, this Master Theorem that we mentioned, or the formula that by just simply expansion of that, you can get this formula. So T of n plus 1 would be 2 to the n, it would be order. So it would be essentially an exponential function that we have it. Now, this is a good example of this one. Let's see another example, which is a bit more complicated, but it has actually applications for let me clear everything. Yes, so let's see a bit more complicated example. That algorithm, actually, this is the function that we have. T of n is equal to n minus 1 plus 2 over n I equal to 1 n minus 1 T of I. For n greater than or equal to 2, of course, we need to have the base case, which is T of 1 equal to 0. And this is the running time of so this is the running time of a quicksort. Great. So this is a running time of quicksort that we are talking about. And we will mention that, we mentioned the running time of merge sort and running time of quicksort. Later on, when we say the exact algorithm, then you will see these are the formulas, but we have the formulas from this. It is important. Lots of these papers actually that you were seeing in the computer science nowadays, they are using formulas to analyze the running time, the approximation factor of the algorithm, the number of rounds in parallel algorithms, the size of a space, and all of them are using this formula. So it is very important that you become very familiar with this. Great. So now let's go and how can we do this? The same technique. We try to eliminate the history, but here let's write first t of n plus 1, which is equal to n plus 1 minus 1, 2 over n plus 2. And here I equal to 1 to ti. Great. Actually, this should be n plus 1. Good. Now that we have this formula, of course, we can simplify this one. So what is the issue? The issue here, we cannot do it simply elimination of the history because here is 2 over n, here 2 over n plus 1. So the coefficients are different. We need to make them equal. So to do so, we just multiply both sides here by n. So we are just multiplying both sides of this by n and both sides of this by n plus 1. Just multiply this, guys. See what will happen. So here, if we have n times that, so we have n times t of n is equal to n times n minus 1, because we have n minus 1 here, times n, plus 2 to the sigma of I equal to 1 to n minus 1 t of I. The other one is this one, that we are also multiplying n plus 1, t of n plus 1. Here, this cancels out. So we have n here, n plus 1, and here this will be eliminated. So it will be 2 this. Now, actually, we can subtract these two formulas because now they have the coefficients which are the same. So let's do that. Let's the left-hand side would be this, and the right-hand side would be n plus 1 times n minus n times n minus 1. This is the formula that we have it here. Plus 2 times t of n, because this one is n minus 1. It remains everything except the last guy, which is t of n. So this is the formula that we have it. Now we can, this one essentially simplified. If you just do that, this n cancels out with this n, and then the only thing that remains essentially 2n. So this is the final formula that we have. This minus this is equal to this. Now, from this formula, actually, let's compute t of n. So we can, t of n plus 1. T of n plus 1 would be n plus 1, 2n that we have it. And here we have 2 times t of n and plus this other n that we get it from the left-hand side, and we bring it to the right-hand side. Now, the only approximation that here, or that we are using it, we say that this formula we are using 2n over n plus 1. This we know that it is always less than or equal to 2. Actually, as n becomes large, that would be the limit of this. So that would be essentially the limit would be 2. So in some sense, for large n, it is exact. For the smaller one is a upper bound. But anyhow, so we just say less than or equal, but I think that's the only place that we are using less than or equal. We could actually say for large n, this is equality. So there, in this case, we have this one, 2n over n plus 1, that is at most 2. And how much is remaining? N plus 2 plus over n plus 1. So from this formula, from this, all this complicated formula, we got this formula, which is a nice. So let's now erase everything. So we have this less than this. Well, as I mentioned, it's equal actually for large enough n. Now, for this one, we can actually, let's try to expand it. So for Tn, we have this one. Again, we write it down, the same formula, 2 plus n over n minus 1, t of n minus. Let's expand it again one more time. It would be, instead of Tn, we are writing this formula. We have 2 plus n minus 1 over n minus 2. And finally, if you expand this one, at the end would be the case that for t of 2 would be equal to, I mean, you just write t of 2 and t of 1 is equal to 0. So in that case, we get the 4/3 at the end. Good. So this is the one that we are doing it. Now we need to simplify it and get the idea. So this is the part that is a little bit, more thinking. But here, just mainly expansions and get the guess again and get the idea. So here we have the first two. We just write it down. Then this n plus 1 over n times 2. So we have this constant there. This other one, it would be, okay, now this guy times this guy. So this will cancel out this when we multiply that. N plus 1 over n plus 2. And then what about t of n minus 1? Here, t of n minus 1 has this other 2 that we want. So in some sense, this is the, when you multiply this guy, and this guy canceled, and this one over this guy times 2. That's the thing that we have it. Plus 1 over n over n minus 1, and this 2n cancels. Now you can actually continue this one. Then the next one would be n plus 1 over n times over n minus 1 times n minus 1 over n minus 2. And here, as you will see, this will cancel out. But remains 2 times n plus 1 over n minus 2. And you will just continue this. So when you do this one at the end, the last term would be this 2 times n plus 1 over n over n minus 1, and so on and so forth. And everything gets canceled except this last things. So it becomes the only thing that remains will be 2n plus 1 over 3. That's the last term that we have it. All others are this one. So it is actually a nice formula now. 2 plus 2 over n plus 1. Instead of this 2 also, we can write it 2 times n plus 1 over n plus 1. So we have this exactly this formula from here. So we can factor out this 2 times n plus 1 times this other guy, 1 over n plus 1 plus 1 over n plus 1 over n minus 1 to 1 over 3. Now, here we are using this formula that we call them harmonic numbers. And what is a harmonic series? This is the hn equal to 1 plus 1/2 plus 1 over 3 to 1 over n. And this is actually the exact formula for this one is h of n is equal to ln of n plus 0. This is somehow gamma is constant or Euler formula. And then this is little o of n. So essentially it is ln of n. And how can we get it? This is the one that we can get it by summations. We can actually approximate it by integration. We will talk about it in the next session on that one, how we can do these integrations and get a formula out of it. But this is the exact thing that you can do it. So h of n is equal to this. And so we have this, we will talk also next time that when we have it 1 plus 1/4 plus 1 over 8, this is important. If you have this one, if you go this one, if you don't have all the terms and you have this one, this is actually goes, becomes equal to 2 and goes to infinity. However, or it is less, would be less than or equal to 2. However, when we have h of n, we have the full term plus here 1/2 plus 1 over 3 plus 1 over 4. So we have some eliminations here. Then actually the gross would be ln. And we are also discussing previous time, when we talk ln of n, this is order, this is the same, this is the order of log n, which is base 10, or which is the order of, sometimes we say lgn, that means log 2. But anyhow, when we talk about ln, log, and LG, all of them are the same within some constant factor. As we discussed previous time, so as we discuss next time, so these formulas, the base is not important. Base only adds a constant factor. So anyhow, so this formula means that here, the exact formula that we have it for this one is 2n plus 1. Here, h of n plus 1, because of this series that we have, minus 3/2, because we are just reducing here 1 and 1 plus 1 over 2. So that's the exact formula that we will get it. As I mentioned, the only approximation that we are using here is this one, that for large n actually it is equality. Now, when we have these formulas, then it is called the harmonic series. And here by integration, you can show it is that. So what do we have as a formula here? The formula that we have it, this would be h of n plus 1, which, as I mentioned, it is essentially log n or ln of n times n plus 1. So we know that actually at the end, so this is the exact formula for that, but if you want to approximate it, would be n times log n. So this Tn would be n log n. As I mentioned, this T of n is actually the one that we are discussing. That would be the running time of quicksort. And this is the good approximation that we will get for it, n log n. And this is some kind of a recurrence formula. So always when you have this kind of recurrence formula, you try to guess what's going on. You try to simplify it. This kind of elimination is very useful, such that you can get some formula, as I mentioned. By elimination alone, we could get such a nice formula, and then we simplify it to this one and some approximation. So these are all the techniques that are working, and then we are expanding it, and we get the results that we want. Next time, I am talking a little bit about some other formulas that we are using. These are like the things that are useful for our purpose of this class, or any other papers that you are writing or reading, essentially, in computer science. And yes, I think that's the technique. So you should work more from the assignment that you have, or these books that exist, especially Introduction to Algorithms by A Creative Approach by UD members, or the other one, CLRS. These are several examples that you can do it, and you become more and more familiar with this kind of relation. And as I mentioned, the recursions are very important, because recursion and induction goes hand by hand. And the same way that we design recursive algorithm, we can analyze them by induction, or the same way that we are doing the induction, we can write the algorithm by recursive algorithm. But to analyze them, you need to use this kind of recursive formula, and you need to be familiar with that. So we have gave some general techniques here, and also some general theorem like Master Theorem or Akra-Bazzi theorem. Good. So if there is let me clear everything. If there is no further question, I think we can finish the recording by here, and then we will talk about more formulas, and then we are starting about some kind of data structures that are used, and we talk about this one in C++ or Python, the corresponding thing that we have there, so that we talk next time about them. Good. If no question, I think we can just finish the class. Thanks. Bye.